Two masses with a mass ma equals 1 kilogram and mb equals 4 kilograms are sitting on a level ground with a compressed spring in between, as shown in the figure here. The system is then released, allowing the spring to restore its original length and the two masses to separate instantly. The spring's potential energy of 10 joules is completely converted into the kinetic energy of the two masses. The kinetic friction coefficient between the ground and the two masses is uk equals 0.2. After the two masses separate, how long does it take to stop the masses? So first we have some equations here. The first one is the equation for kinetic energy, which is 1/2 times the mass times the velocity squared. Second is for momentum, which is equal to the mass times the velocity. The third is the momentum impulse theorem. It states that the force times a change in time is equal to a change in momentum. And the fourth one is the relationship between kinetic energy and momentum, which says that the kinetic energy is equal to the momentum squared over 2 times the mass. This is found directly using these two equations here. Okay, so first we need to figure out the amount of kinetic energy that is transferred to each block. Now we know that the momentum that is given to block A is equal to the momentum that is given to block B. Now this diagram is actually a little off. B is actually supposed to be the bigger one, so, well, this is just a relative drawing of how they're like. So we know that their momentum will always be the same. The momentum of A will be equal to the momentum of block B after they separate, but their kinetic energies are not necessarily the same. So let's figure out the kinetic energy of A. The kinetic energy of A, simply its momentum. I'm not going to write any subscripts for this since we already know that their momentums are equal. Divided by 2 times its mass. Same thing for the kinetic energy of B. Sorry, it's B squared. Now we can just plug their masses in, which is simple enough. You have P squared. The mass of A is 1 kilogram, 2 times 1 is 2. This is equal to P squared over 4 kilograms, 2 times 4 is 8. And then here you will notice something about these two kinetic energies. The kinetic energy of A is actually equal to 4 times the kinetic energy of B. This is because if you multiply this by 4, you'll get the same expression as the one up here. So we know that the kinetic energy of block A is 4 times as great as the kinetic energy of block B. So now we can actually go ahead and solve for the kinetic energies here. So we know that the kinetic energy of A is going to take 4/5 of the total kinetic energy of 10 joules. This is because it is 4 times the kinetic energy of B. And the kinetic energy of B is the remaining kinetic energy, or 1/5 of the total of 10 joules. Now if you simplify this, the kinetic energy of block A is going to be 8 joules, and the kinetic energy of block B is going to be 2 joules. So now we have figured out the kinetic energy of this. Now before we can figure out how long it will take to stop the masses, we should probably figure out the velocity of the masses when they first leave the spring. This can be done by simply manipulating this kinetic energy equation right here. So the kinetic energy is equal to 1/2 times the mass times the velocity squared. We can manipulate this to say that the velocity is equal to the square root of 2 times the kinetic energy divided by the mass. It's by simply multiplying the kinetic energy by 2, dividing by the mass, and then square rooting that whole side. It's a basic algebraic manipulation there. So now we can solve for the velocity of each one. The first one, we have the velocity of A right after leaving is the square root of 2 times its kinetic energy divided by the mass. This is the square root of 16, which is equal to 4 meters per second. Now the velocity of B, again we do the same thing. We plug their kinetic energies in, which is 2 times 2, divided by the 4 kilograms of its mass. And then this will give you the square root of 1, which is simply 1 meter per second. And now we have figured out the velocities of the two blocks. So I'm going to rewrite this up there. Then we know that the velocity of block A as soon as it leaves the spring is equal to 4 meters per second. And the velocity of block B as soon as it leaves the spring is equal to 1 meter per second. Now we can use our final equation here, which is the impulse momentum theorem. And this simply states that the force times a certain times interval is equal to the change in momentum. Now this force will be the friction force acting on it that will be slowing it down. The time interval is how long it will take for that block to come to a complete stop. So you can write that the force of kinetic friction times the time interval of A, so let's start with block A, is equal to the change in momentum of block A. Since block A is going to be losing all of its momentum, we can just simply write its momentum of the mass of A times the velocity of A. Now we already have figured out the velocity. Again, the force of kinetic friction is equal to the coefficient of kinetic friction times the mass times the gravity. So we can just substitute in. So the force of kinetic friction is equal to the coefficient of kinetic friction times the mass of A times the gravitational acceleration times the time interval times the time that it takes to stop. And we can equate this. And then again, we don't need the mass. So I'm going to make a general equation here. So we're solving for the time. So the coefficient of kinetic friction times gravity times time equals velocity is what we have right now. Solving for time. So we know that time is equal to the velocity when it first leaves the spring divided by the coefficient of kinetic friction times the gravitational acceleration. And this is the equation that we can use for both blocks so that we don't have to go through all of this again. So if we erase that, and then we plug in the time for A is equal to its initial velocity divided by the coefficient of kinetic friction of 0.2 times the acceleration due to gravity. And then this will get you about 2 seconds. So the time it takes for A to stop is about 2 seconds. I'm gonna write this. The time it takes for block A to stop is 2 seconds. That's the first part. Now we do the same thing for B. The time it takes for B to stop is equal to its initial velocity once it leaves the spring of 1 meter per second divided by the coefficient of kinetic friction, again 0.2, times the acceleration due to gravity. And this will get you about 0.51 seconds. So the time it takes for B to stop is equal to 0.51 seconds. And that is how long it will take both of the masses to stop.